Okay, I'd like to talk now about the relationship between P and NP. So let me write that down here. So P versus NP. So both P and NP live inside the set of decidable languages. But I want to talk a little bit more about the relationship between the two. So if I go back to these problems here, I know that these problems in NP can be verified in polynomial time. But it's not so clear that they can be solved in polynomial time, right? I mean, I can make a naive algorithm that's for the Hamiltonian path. I would say try all n factorial permutations and verify them. So I came up with, an n squared verifier, so that would all in all take big O of n factorial times n squared time, which is terrible. That is not polynomial time, right? We already talked about how exponential dominates polynomial and factorial dominates exponential. So n squared times n factorial is certainly not polynomial time. But how do I know I didn't miss some much better algorithm for doing Hamiltonian path? So that's a question. But the naive algorithm doesn't seem to be very promising. And we'll have a similar issue for independent set. Now, in this case, like I said, the size of k, so the size of the independent set, could be chosen to be on the order of n. And so what I'd really be looking for here is, a naive algorithm would try all subsets of size k of the vertices and verify them. Well, all subsets of size k, suppose, like I said, k could be in the order of n. Suppose k is equal to n over 2. And so that's kind of the most subsets I could possibly have. So that would be n factorial over n minus k factorial. So that would be n factorial over n over 2 factorial squared, quantity squared. So that is almost as bad as n factorial. And then we're going to do an n cubed verifier on top of each of those. So that's not very good either. But again, it's a naive algorithm. I'm like, oh, is this an independent set? Is this an independent set? Let me try. In the example that I showed, I'd be trying all possible subsets of size 6 here. So it's not clear that NP can be done in polynomial time, at least not on these problems, even if the solutions can be verified in polynomial time. But one thing that I can say it's a little bit easier to say is that every problem that's in P is in NP. So what I mean in particular, so I guess I'll say this is a lemma. A problem in P, so proof here, a problem in P can be solved in polynomial time. A problem is in NP if I can find a polynomial time verifier for it. So let me construct a polynomial time verifier for this problem. So let's say I have some problem P. So I'm supposed to pass along a string and a certificate. Well, what I'm going to do is just ignore the certificate and solve the problem. So for example, if this was the language, L is equal to W hashtag W, given W is a string in the language, or a string over the alphabet. Well, fine, I can make a verifier for it if you want to go that route. I'm just going to ignore the certificate and just run my Turing machine on W, solve the problem, and accept the verifier if the problem is, accepts, or reject if the problem rejects. So certainly if I go back to my definition of NP, there exists a certificate so that this verifier accepts W in the certificate if W is in the language. Well, any certificate would work. I could just put bogus in there because I ignore it. So what this shows is that, if I were to write it down using set notation, I would say that P is a subset of NP. Okay, So if I'm drawing the picture here, I know that P and NP are both decidable languages. What I've managed to show so far is, okay, so NP is a decidable language, so I know that that's a subset of decidable languages. NPs are all decidable. What I've shown here is that P is a subset of NP. So here is one hypothesis, that P is actually a strict subset of NP. But a moment ago, I did sort of say that, well, even though I looked at these specific examples that are in NP and they seem like they're probably not NP, we don't actually know for sure. So another hypothesis is actually that not only is P a subset of NP, but that NP is a subset of P. In other words, if I'm in NP, then I can solve U in polynomial time. So let me show you what that hypothesis would look like. So the second hypothesis is simply that P and NP are the same. And so I would just show it like this. I would say P is equal to NP. And amazingly, nobody has managed to rule this out yet completely. After decades, really, of trying this. So, but I think most people believe that hypothesis 1 is true. Just because, I don't know, first of all, it's gone on for a long time. Also, these problems are really hard. Like, especially other problems in the NP class, they're really hard. And I had an instructor once say that if P was equal to NP, then aliens would have already taken over us because they would have figured that out and they would have solved a lot of really hard problems using polynomial time algorithms. So it doesn't seem like P is equal to NP, but we don't know for sure. Okay. But what is much easier to show is that P is a subset of NP. I can at least show that direction by making this kind of stupid verifier that just completely ignores the certificate, right? And it'll run in polynomial time because I can solve the problem in polynomial time, right? This runs in polynomial time. So it's in NP. Okay, but so does that mean, what does NP stand for then? Does NP then stand for not polynomial? No. Which is very confusing, okay? Because you're like, well, because it could be polynomial. So why does it stand for not polynomial? NP does not stand for not polynomial. It's such a pain. I hate that they call it this. I mean, I guess it kind of makes sense once you get used to it, but when you're first learning it, it makes no sense. So NP actually stands for non-deterministic polynomial. Okay. So we can verify something in polynomial time, and that means it's an NP. Another way to define the class NP is a problem is in NP if it can be decided in polynomial time on a non-deterministic Turing machine. Okay. So what I need to prove is that, so to prove is that a problem is in NP by my definition up here, if and only if that problem can be decided in polynomial time by a non-deterministic Turing machine. Okay, so that's the claim here. And then that's why NP will earn its namesake as non-deterministic polynomial. Okay, so there are two directions to the proof here. The first direction assumes, so given a NTM M that decides our language in time O, we'll say O of n to the k, we want to show that we can construct a polynomial time verifier, in particular an O n to the k time verifier. So given this non-deterministic polynomial definition, let me show that I can construct a polynomial time verifier. Well, so back when we were doing when we were showing the reduction from a non-deterministic machine to a deterministic machine, we showed how we could use breadth first search to keep track of the different branches of the computation. So basically, a certificate identifies one branch of the non-deterministic Turing machine M's computation. So we'll run the NTM just on that branch. So remember that was how we were able to simulate a non-deterministic Turing machine. So just run the non-deterministic Turing machine on that branch because the NTM was polynomial time. Then each branch runs in polynomial time. So therefore, the branch corresponding to our certificate runs in polynomial time. All right. So if we have a non-deterministic solver, then we can just basically pay attention to one branch of that solver, which is going to run in polynomial time. The second direction is, given that we can verify, so the first definition that I gave, given that we can verify L in O and K time, show that we can construct an NTM that decides the problem in polynomial time. Well, in this case, we just non-deterministically select strings as inputs of length no more than big O of n to the k, and run the verifier in parallel on each of these strings. And if one of the branches accepts, we accept the whole thing. And since we never selected a string that was too long, this whole thing will run in polynomial time. And so it's like saying go back to your independent set or whatever, and basically just non-deterministically try all subsets in parallel. And because it only takes polynomial time to verify each subset, then the entire parallel running string will run in polynomial time. So that's another way to think about NP. It's the set of problems that can be decided in polynomial time by a non-deterministic Turing machine. But unlike when we were just showing equivalence and decidability, when we showed the reduction just for decidability of a non-deterministic Turing machine to a deterministic Turing machine, when we're focused on time complexity, we're not really sure if the reduction preserves time complexity. So all that we can say for now is that, I don't know, polynomial time verification, it's at least as strong as polynomial time, but we're not sure if it's at most as strong as polynomial time decidability. So that's all I have for you for now on that stuff. Basically what we're going to do in the rest of the course is study a bunch of problems that are in NP that we think are probably not NP. So these are called NP complete problems. So when we get back from break, I will define those, and then we're just going to study a whole bunch of those different problems, and then I'll even show you how to code up some solvers for them. Even though it seems like they're we can't solve them efficiently, there are things we can do in practice to try to solve them. So I'll introduce something called the Cook-Levin theorem, and we will explore this actually in code and in a very practical way. So I'm really looking forward to this. This is what the course is going to culminate in, and I hope you enjoyed it as much as I did when I learned it, and as much as I do teaching it. So enjoy the rest of your break, and I will see you soon.